Blade Runner is a fantastic cult science fiction film, and one of the best moments in it is when replicant Roy Batty delivers this monologue as he accepts his death because he's an artificial being with, by design, a limited lifespan.
I've seen things you people wouldn't believe. Attack ships on fire off the shoulder of Orion. I watched sea beams glitter in the dark near the 10-house gate. All those moments will be lost in time. Like tears in rain. Time to die.
Some say that is the greatest soliloquy in cinematic history. But a lot of people don't realise that it touches on a paradox of what physically happens when tears and rain come together, the so-called mixing paradox. The mixing, or Gibbs paradox, is about how entropy may or may not change when you mix two similar things together. Now, it's normally stated in terms of ideal gases, but we'll talk about tears and rain in this video, so essentially water. Let's actually show them in a box separated by a partition, with tears on one side and rain on the other to start with. To get to the paradox, first we need to know what entropy actually is. It provides a link between the microscopic and macroscopic worlds. Essentially, it measures the number of different ways that you can arrange the microscopic properties of a system, say like the positions and velocities of molecules of water, that would end up giving you exactly the same macroscopic system, so the same density, temperature, pressure, etc. In fact, technically, the entropy is the logarithm of this number multiplied by some constant. Throughout this video, I'm just going to demonstrate the concept of entropy using what's called the configuration entropy. This only uses the positions of particles. Also, for simplicity, I'm going to limit the number of positions to just a few distinct locations. Neither of these are actually problems. You'd come to exactly the same conclusions if you treated entropy more generally. So what happens when we open up that partition and wait for the tears and rain to mix? What happens to the entropy? Well, surely it goes up. It's easy to show that there are more ways of having a mixture of tears and rain on both sides of the box, compared to just having tears on one side and rain on the other. The second law of thermodynamics states that entropy shouldn't decrease unless we externally act on the system. So another way of thinking of whether the entropy has increased is to ask, do I need to do anything to get back to the original scenario? And the answer is clearly yes. I need to move all the tears over to one side and the rain back over to the other. So the mixture must have a higher entropy than we started with. But what if tears and rain aren't actually different? What if they're the same, just water? Then by mixing the two sources of water, does the entropy change in this case? Well, surely not. I could close the partition at any time and still have exactly what I had to start with, water on both sides. I don't have to put any extra energy in to revert back to the original. So the entropy can't have changed. But this is where the paradox comes in, because in the case that tears and rain were different, the entropy increase when the two mixed was fixed. It doesn't actually depend on quite how different from one another tears and rain actually are. So we could prepare tears and rain that are almost but not quite indistinguishable, and we'd still get that increase of entropy. Whereas if they were completely indistinguishable, entropy wouldn't increase at all. This doesn't really make sense. It's a paradox. But there is a resolution. If we can treat tears and rain as similar, even if in reality there is a way of distinguishing between them if we do a very detailed experiment, so long as we don't do that experiment, we can label tears and rain as being the same thing, water. And we don't get an increase in entropy. Even if, in fact, tears and rain were physically different. It's how we label them that causes there to be either a change in entropy or not. Or in other words, entropy is subjective. So if the particles are experimentally indistinguishable from one another, then the paradox is simply resolved. And thankfully, quantum mechanics gives us extra reassurance because, in principle, all like particles are completely indistinguishable from one another. This comes about because of how quantum mechanics operates. Say we've got a set of particles and we're observing them over and over and over again to try and track their trajectories. But in between those measurements, those particles do not have well-defined positions. They're governed by wave functions. Wave functions have a tendency to spread out over time when not being observed. And if they start overlapping, you can no longer determine which particle went where. They are indistinguishable. Thanks so much for watching all of this video. I hope you enjoyed this paradox, sort of inspired by Blade Runner. Let me know in the comments, do you think Deckard was a replicant and why? And if you haven't already, please do subscribe to my channel to make sure you always get the latest video. See you soon.